Good morning. So today we are going to look at one-dimensional maps. So essentially, this is a very simple paradigm to study chaos. So essentially, a one-dimensional map is given by a single valued function and the future iterates are given by application of the function to the initial conditions. So one can have the future iterates would be application of twice to the initial condition, so on and so forth. Here you can regard n as the time step where the time now is discretized. And the trajectory consists of the time series, which is going to be the points upon the repeated application of the map. The fixed point, by definition, would be something of this form. We apply the map to the fixed point, it again gives us the fixed point, so on and so forth. This would be equal to application of the map twice equals to any number of applications of the map. One important construct regarding any dynamical system is, of course, the fixed points. What happens to the trajectory in the neighborhood of those fixed points? So for that we see the stability analysis of fixed points. So in a way, the fixed points you can regard as when you do curve tracing, when you sketch any function going beyond dynamical systems, you have the roots of the function or where the function is zero. That's a nice way to get a qualitative idea of what happens to the function. Similarly, for a dynamic system, whether it's a map, it's given like a flow, it's always nice to see where the fixed points are, where the trajectory won't go anywhere, and also what happens in the neighborhood of fixed points. So by neighborhood, I mean, let's say some variable or some value near the fixed point. X star is my fixed point. Somewhere close to X star would be my value. And what happens is when I apply the map again, I get x n plus 1. So as usual, I have, and writing it this way, I get the fixed point, the value of the map at the fixed point, plus how much is the error, you can say, epsilon n plus 1. So that pattern, how epsilon n compares with epsilon n plus 1, tells me what is happening. So for example, I'll again write it. And this, I write it as this guy, and which is equivalent to now since this is a fixed point, this is value cancels with this guy, and I'm left with the so depending upon whether is greater than 1 or less than 1, uh, epsilon n is going to be greater or less than epsilon n, or uh, the point on the map in the neighborhood of the fixed point, either it's going to go away from the fixed point or it's going to shrink back towards the fixed point. So this is entirely governed by the first derivative of the map at the fixed point, and this is known as linear stability analysis, where we are interested in how the map behaves to the first power in the error. And of course, first derivatives are involved. What happens when f prime, which was at the fixed point, is equals to 1? And this is known as marginal stability. And we would require higher orders to gauge whether or not this fixed point is stable or not. So the first derivative being less than 1, all the points in the neighborhood of the fixed point are going to come back to the fixed point, and that's called as a stable fixed point. Stable fixed point. So this is essentially how we analyze the stability of fixed points. And as an example of a map, let's consider the logistic map. This is a very popular one-dimensional map used heavily in ecology, population biology, so on and so forth. So the logistic map is given by this equation. Uh, as you can see, it's a nonlinear map where the nonlinearity is uh, of quadratic nature. I get a power of xn square over here, and x ranges from 0 to 1, and the parameter r goes from 0 to 4, and this ensures that the map gets mapped to 0 to 1. So this shows that the map gets mapped over and over again to this limit 0 to 1. So diagrammatically, we have this is xn, this is xn plus 1, and let me draw the sketch of the map, and this point is the map attains the maximum at xn equals to half, and this is point is r by 4 over here. So for any value of r between 0 to 4, this map will get mapped back to the interval 0 to 1. Why this is such a elegant example to study a phenomena of rich behavior is that, of course, you can throw the entire physics out of the discussion and just keep iterating this map on a simple calculator. Uh, so let's see what happens when we do that. So let's say we fix R. We fix R. Let's say R is 0.5, and we have some initial condition x0. That's my initial condition. So I'll get my future iterates. So on and so forth. So what happens when I sketch? So this is my xn, and as I have 1, 2, 3, n. So I start with some initial condition, and as I'll see the subsequent values, that just dies off. It dies off. So as xn goes to 0, sorry, xn goes to 0 as n goes to infinity. Of course, 0 indeed is a fixed point. As you can see from the map, I put in 0, I get 0 back. So 0 is a fixed point. But it seems to be a stable fixed point because every trajectory goes to 0. Compare that to, we are going to come to this picture in a minute. Compare that to what happens when r equals to 2.8. So again, you can do this experiment on your calculator. So I have, once again, n, and I have the iterates. So as you will see, this guy goes up, comes down, follows, and these are only just rough sketches, but this is what happens. The trajectory chooses another fixed point. So xn goes to x star, some other fixed point given by this, as n goes to infinity. This is the fixed point. Starting from some initial condition, it hops around, some transient motion occurs, and then it zeroes down on another fixed point. And this fixed point x star does not depend upon the initial condition x0. Of course, as long as my initial condition is not 0. And what else? It's not 1 either. If you look at this map, in some sense, x star equals to 0 or x star sum equals to 1. These are my fixed points, which is obvious. But starting from any other point other than these two trivial fixed points, I zero down upon another fixed point that doesn't seem to depend upon the choice of my initial conditions beyond x0 or x1. So let's look at another case. What happens when I have the same map I have the same map and I am analyzing it at r equals to 3.5. So again, I have this is n and this is my what happens to xn iterates. I go some sort of a trajectory, and finally I settle on a period 2 cycle. And these oscillations persist. So the magnitude here at xn and at xn plus 2 is the same. It's following a discrete periodic orbit or a period 2 cycle. And this is like much like the limit cycle for continuous time dynamical systems, what you've already seen, a glimpse of it in the class. And sorry, so this was probably at r equals to 3.3. Maybe you should do these experiments on your calculator and see what I'm saying is true. So for r equals to 3.5, you run this map on a calculator, and what do you find? This guy, after a while, settles on I'm not drawing it quite well, but you get the idea. Let me again have it. So I have 1, 2, 3, 4, 1, 2, 3, 4. Let's erase this map. We all know what the map is. I'm just going to write it over here. Yeah. So this is, in some sense, if you look at it, this is a period 4 cycle. Where what is happening is that I'm going hugely up, then I'm going down, then 2 middle points, then I'm going up, then going down, completely down. So these are all repeat xn, xn plus 4, xn plus 8. So these are all in one line. So it's a periodic 4 cycle. And notice the period of my attractor, or where finally the trajectory settles down, has doubled. So I go from period 1 to period 2 to period 4. Period 1 to period 2 to period 4. And as I keep on increasing R, notice R was increasing, R at 3.3, R at 3.5. As I slowly keep on, let's say I have a switch or a knob where I'm keeping increasing R, I'll find that the attractor increases in period. And one may ask, where does it go? So remarkably, at certain discrete values of R, period doubling occurs, period 1, period 2, period 4. So period 2, period 2 to the power of 2, period 2 to the power of 3, and it goes all the way to infinity. So, of course, one of the questions is that where exactly does, at what values of r, this period doubling occurs? That is from 2n, I go to 2n plus 1 period. Of course, we are going to answer such questions. Second question might be, what is responsible for this period doubling? Of course, we know that we are cranking up r, the parameter, and a remarkable thing is that this period doubling essentially is a very universal phenomenon, in the sense for any map. Of course, we dealt with the logistic map, but any map with a hump shape, qualitatively speaking, so qualitatively speaking, any map with a hump shape will show this period doubling behavior. And qualitatively, the analysis is going to be exactly like the logistic map. So this is when I talk about universality of such 1D maps. As physicists, we are always interested in where all we can take our simple toy models and how universal they are. So this is something very remarkable. And you also notice such a behavior, as I said, in any map with a hump shape is going to give you such behavior. Now, let's analyze our second question, which is like, let Rn, what values of R? Is there anything special about the values of R at which this period doubling is occurring? So Rn is the value of R where this cycle occurs. So by it I mean R1 is the point where period 1 cycle, I find a period 1 cycle, and as I know, R1 is 3. Sorry, yeah, so R1 is a period 2 cycle, so that means I have a period 2 cycle. That, by that I mean 2 to the power of 1 cycle, 1th cycle occurs. R2, where I get a period 4 cycle, that occurs at 3.449. So I get a period 4 cycle, it's 2 to the power of cycle, 2 cycle. R3 occurs at 3.54409 something approximately. Here a period 8 cycle occurs. Similarly, R4, we get a period 16 or 2 to the power of fourth cycle occurs. R5 is where 3.568759, so period 32 cycle occurs. So what do you notice in this trend? Well, of course, the values of R are converging. Slowly, I get the distance between the subsequent period doubling is shrinking. And we'll find that R infinity and infinite cycles occur at 3.569946 somewhere. So essentially RNs are converging, and I can plot them. So I have Rn minus 1 over here on the number line. I get Rn. Then the distance between Rn and R plus n plus 1 is lesser. It's even lesser and lesser, lesser. Finally, this is R infinity. So I have, as n goes to infinity, this number, as n goes to infinity, the distance between the n minus 1th cycle, nth cycle to n cycle to n plus 1th cycle, that goes to 4.6692 some number delta, which turns out to be a real rock star in some sense. So this number is something like a kind of a very interesting constant, like the number pi, you can say, or something like that. But this number actually also captures how the subsequent points at which I'm going to find a period 2, period 4, period 8 cycle is going to shrink. It's going to converge, and that number is a constant. It's called as the delta. So now one might ask the question, what happens beyond R infinity? Well, the answer is a lot of interesting stuff. So over here is a sketch to make you appreciate what's happening. So this is taken from Edward Ott's book. So over here is R, the parameter, and out here is X, of course, what happens to my trajectory after it has settled down on an attractor. So how my algorithm looks, how do I get such a curve? What's the algorithm? Well, I start with a particular R. Let's say R here starts at 3.5. So set R at 3.5. Set my initial condition at, let's say, a value of half. And I iterate, let's say, for 500 times. Iterate for 500 steps. And I'm going to throw them away. I'm going to ignore these iterations because that allows, I'm interested in the long-term behavior. As I keep iterating, what trajectory, what period cycle, or what attractor does my trajectory settle onto? And after throwing them off, I iterate again for, let's say, 1000 time steps. and I plot them. This is essentially this plot. Remember, all this is happening to this map. And then I increase my R by a very tiny fraction. And then I return back to step 2. I pick another initial condition, again the same initial condition. I throw away the first 500 iterates and then plot. So return to step 2. So this goes back to step 2. So when I do that calculation and I plot my graph, this is what I get. You notice that slowly the period is doubling. This is a period 4 thing. It becomes a period 8 thing slowly. This is going to become subsequently reach R infinity, which is my point where my R infinity or periods have doubled from 2, 4, 8, 16, 32 to infinity. This is my R infinity. And I've just been here, somewhere here, which was 3.569946, this guy. So this is 3.569946, da, 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 da. And you see, there's a whole range of interesting phenomena happening over here beyond R infinity. So let's say if you look at, we go work backwards looking here at R equals to 4, it seems that the entire 0 to 1 range itself is an attractor, and it's an aperiodic attractor. And it contains the whole range. And this is also, we'll find out, a chaotic attractor, which will be very sensitive to initial conditions. But as we fix R at 4 now, first initially we were going this way and we were finding the period doubling. Now let's say my switch it at R equals to 4 and I keep coming down, shrinking my R, reducing my R. You look at the point B, which is somewhere less than 4, but still it's on a completely chaotic attractor. But you see the range is also shrinking. So this is an entire range. This range is shrinking. If you look at it. So at a certain value of R less than 4, this has become, is not quite from 0 to 1 as it was here, from 0 to 1. It has shrunk. But still, I find myself on a chaotic attractor with one wide band of range over here. Notice at C, I am somewhere, if you can look at it, this is my attractor. My attractor has 2 bands. So that would be somewhere, if you look at it here, this is band 1, this is band 2, something like that. And the trajectory is going to hop, 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 alternatively on the bands. So you can see that's such a rich range of phenomena happening. Not only that, you see these ranges. So for example, over here, you see these windows. And these windows are so interesting. So over here, if you look at this window, this is a period 3 window, 1, 2, 3. And this period 3 window is going through its own period doubling, so on and so forth. So I'm going to zoom in this period 3 window, very roughly speaking. So it looks like let's say it's going to have its own period doubling story. So this is a zoom in of period 3 window. And remarkably, it would have its own R infinity, something beyond R infinity with its own period 3 window again, inside a period 3 window, somewhere here. So in other words, I'll have a very self-similar structure if I zoom in on this guy, the period 3 where it starts. It's going to have the copy of the entire bifurcation diagram with its own period 3 window. And this is not true for just a period 3 window. I'll have, you give me an integer, let's say 19. Remarkably, I have a period 19 window. So somewhere here, I also have a any integer. Let's say somewhere here in this map, I'll have a period 19 window, period 17 window, so on and so forth. And that period 19 window will have its own period doubling. And they occur in a certain order. Not in a sequence, they occur in a certain mysterious order. We'll come to that later. But the bottom line is you give me an integer, I'll give you a period doubling window starting from that integer. So this is quite remarkable, and it has a beautiful cell structure. It's almost like a fractal over here, that I have a period 3 window here. Inside this period 3 window, somewhere after reaching R infinity, I'll have another period 3 window within this period 3 window, so on and so forth. So, and this is all happening as a function of R, which was the parameter of my map. So once again, to see what really is happening as far as my, where is exactly this sort of a bifurcation happening, we are going to study it in the next lecture.